Hopefully corporate America will start taking notice. So what you're going to see tonight is an approach to cybersecurity that essentially says your machines will be penetrated. Doesn't matter what you do, they're going to be penetrated. So now the question is, how do I survive it? How do I protect my information? How do I keep my critical systems running? And that's the nature of what I'm going to present. It's not going to prevent an attack, because in effect, if you stop to think about it, how many people are programmers here? Okay, so you know that most systems that do anything significant, if you collect the applications, the OS, the support software, the tools, the whole business, there are millions of lines of code. Millions of lines of code. So if you think about a sheet of 8.5 by 11 paper having 100 lines, take something like Linux. I'm going to guess Linux is going to be somewhere between 10 and 20 million lines of code. Those sheets of paper are going to fill this room. And that's not prose. It's code that's very detailed, very complex, and you know there's going to be bugs in it. Bugs are a fact of life. And the systems are getting larger. They are not getting smaller, they're getting larger. And they're written by humans. Now there's all kinds of software that's being produced to help reduce the incidence of bugs, but in the final analysis, bugs are going to be a fact of life with software. I think most software engineering people recognize that, and they do testing, validation, and debugging. But of course, debugging says you're going to find a bug, fix it, but it doesn't say anything about the absence of bugs. So given that, how can we protect our intellectual property and protect our systems as they're running? Now, I'm sure a lot of you, if not all, have gotten infected, and the infection has rendered your machine useless. You just couldn't use it any longer, which is bad enough. But imagine now that is an aircraft system. Aircraft systems these days are all software driven. Anything that's digital, running a program, is hackable, and it will be hacked. There was a university group that did the work on cars, and they were able to hack into a car that was placed in a parking lot and take control of it, follow it in the streets, stop it, start it, control the accelerator. Now, cars are one thing, but imagine that the next wave of terrorists take over aircraft. When that aircraft pulls into the hangar, you know that technicians are walking up to that aircraft with laptops to do testing, or machines that they have in the hangar. They're going to plug in either through an internal network. For military aircraft, the internal bus network is something called 1553. In civil aircraft, it's another bus architecture. They're going to tap in and talk to the various systems or load parameters. For military aircraft, they're going to load up mission parameters. So machines are becoming highly digital. It's not a surprise, but also they come in contact with other machines and you don't know where they've been. So there's lots of opportunities to infect machines. So now let's move on. This is another kind of a property versus implementation. I'm going to skip over that. So here's our approach. Our approach, and I'm going to cover each of these in detail, says we're going to provide a fortification, a protected, a logically and physically protected computational enclave. And that's symbolized by the monolith. Inside that monolith, we're going to have code that runs and monitors and protects, defends the host computer, which this machine is meant to protect. The labyrinth is meant to represent the target's machine's execution environment. And the intent of the labyrinth is that the internals of a running machine, a machine that's executing an operating system, is indeed a labyrinth. But with these two combined entities, not only do we look at the labyrinth, know what it ought to look like, and can detect problems, but when it's under attack, we can change the labyrinth in real time. Now, for those of you who are programmers, you know that there are certain aspects that you don't, it's not part of the programmer's psyche to think that when he lays down a value in a variable, that that value is going to change without his participation. Yet what I'm about to show makes that possible. That is to say, a programmer, whether it's a black hat malware programmer, if they write something out to disk, I can change it on a disk so that when they read it back, they don't read back what they wrote. Same thing with memory. When they paint memory, we can come by, we can notice that they're painting memory and change the color of the paint that they've laid down. In other words, change the code, change the data. And with the architecture that I'm going to show, we can do that without consuming any cycles on the host machine. One of the big problems that people tend to worry about when you talk about cybersecurity, well, how much is this going to cost in terms of slowing down my machine? How many cycles you're going to steal from my execution space? The approach that I'm going to show you does not steal cycles from the host machine because it doesn't run on the host machine. It runs on its own processor. Now, if there are questions, just feel free to break in at any time. Be happy to answer questions as we go along.
As opposed to processor, I'll ask you about that in a minute on the daughter board. So a daughter board to me is a small board that's parallel to whatever board is there or a daughter board. What processor does it use? Shared memory? Is it bus snooper?
Well, I'm going to show that in the
okay.
We'll show a picture of it.
Okay.
Here. All of that. Yeah. It's essentially a power PC. It's a power PC.
And then the first thing that pops into my mind is with the hardware of the different vendors. I mean, don't you have problems being certified to add your hardware onto theirs and then have them?
Well, first of all, we're undergoing a government certification right now. It's 140 level 4, which is one of the highest certification processes. Mm-hmm. So we're undergoing that in terms of cyber security. Now, when we put first of all, it's our intent to sell the machine. Although we're going to sell the board separately, but the way in which I believe we're going to break into the field is to sell a fortified Linux box.
Where they might have Dell,
yeah.
servers. I mean, you have to, I guess you guys are targeting the hardware from certain vendors.
That became the SiCore. He showed us a PCI card with a CPU on it.
Yeah, it's a PCI Express card.
Maybe that'll help you visualize it. So it's a computer that runs on a separate PCI card. This is not that alone is not a new concept.
No, that's an old concept.
Yeah, that's an old concept. But what they're doing with it is different.
And through the PCI bus.
Yeah, the card itself sits on the PCI Express bus.
Okay.
Okay. All right, so the secure coprocessor contains tamper detection capabilities. And I'm going to have a, let's see, here. I'm going to pass this around. By the way, this evening we have all of the major developers of the system here. So if you have very detailed questions, the engineers are here, with the exception of the electrical engineer who just had to leave. But all the other people involved in the design of the system are here. I'd like to pass this around. This is a membrane, and Steve Weingart, who's in the black, is the designer of this. And the intent of this is that you wrap a piece of equipment in this, epoxy it, and it acts as a sensor for someone trying to penetrate. And this is wrapped, it's epoxied, and then anyone attempting to get at the inside of the circuitries will trip the sensor, and the secrets will be erased. And that's to prevent someone from instrumenting the electronics with a logic analyzer, for example, and reverse engineering the machine code, or extracting keys or information from the electronics. So I'll pass this around. And we'll talk about those details throughout the presentation. So there's the penetration membrane, voltage sensors, temperature sensor, X-ray, and there's also an out-of-band hard disk that gets attached to this card. So this card has a disk that it has access to, but the host does not. So, and that, because it's a SATA disk these days, you can connect, we've connected up to a 2 terabyte disk. And it may sound like a small thing, but it turns out to be very important, because that gives us on hand instantaneous access to a pristine repository. So if a component is detected to have become corrupted in some way, we can replace it as soon as the detection takes place. We can replace the file or the sectors of the file, and we'll talk about the details of that. So that's what I was alluding to in terms of near real-time reaction and repair to keep the system running and to reduce the effects of an attack. Now, for those situations where a system may be taken into the battle space, we also have a hardened and instrumented enclosure that says we're going to take the motherboard, put it into this enclosure. It's instrumented. It takes special tools to drill through it. It has sensors inside so that if you try to break into it, it will react. Now, the technology that I'm describing is meant to withstand an attack by a nation state, which means that it is anticipated that if an adversary such as China or Iran gets a hold of this system and takes it to their labs with unlimited resources and unlimited talent, it will withstand that attack and not give up its secrets. So it's probably overkill for a corporate use, but then maybe not. There are companies whose life depends upon their algorithms. One that comes to mind, I think, is Stony Brook, that did the trading algorithms. Those algorithms are the lifeblood of that company, and so, yeah, Renaissance Technologies. I was trying to avoid naming it, but so there are many companies whose life depends upon those algorithms. So this is the type of technology where they could run the algorithms in a protected environment, protected even from insiders. Okay? So this is a block diagram of the card itself. It contains a CPU, it contains memory, and the out-of-band disk that I talked about. There's a field programmable gate array. Those are additional sensors. It's wrapped in a tamper detecting membrane, which is what's going around. So code gets to execute here in a protected environment. And what capabilities this gives you is the following. The FPGA, this is a local bus, and there's a pathway between the PCI Express, this local bus, through the FPGA to public memory. So this memory can be mapped to the host processor's memory. And it can be monitored by an FPGA is a field programmable gate array, which means that we can instantiate logic, specific logic on that chip that is custom made to an application. In addition to that, it's also possible to instantiate on these FPGAs something that's called soft core processors, so that if for applications that warranted, we can instantiate multiple soft core processors on that FPGA and have additional multi-processing capabilities. I'm going to speed up a little bit because I can see it's getting late. So here's what the card looks like. It's a PCI Express card. It's a 4-lane PCI Express. Now, each lane on a PCI Express bus has the capability of transferring 2.5 gigabits per second. So this has the potential to transfer 10 gigabits per second across the PCI Express bus. So 4 lanes. This is the plastic that's coming around. This is what gets wrapped in the tamper detecting mesh. It gets potted and covered in epoxy, and then there's a metal cap that goes over it. Okay? So this gives you a breakdown of the physical protection of the card. All right, so there's let's see. The red line is the plastic form that's going around. The blue is the tamper detecting mesh that is also going around. And then let's see. Here is the potting gets filled in here all around the mesh. This is those ribbon cables that come out, and then there's a metal case around it. Yeah, right here is a SATA connector. And so you connect a SATA cable to a 2 terabyte disk. It's not inside the card.
So how do you know that the disk is not tampered?
How do I know that the disk does not what?
It's not tampered with.
The disk is encrypted. So if it's disconnected, they have to get the key. The encryption key is kept on the card.
Okay.
It can be destroyed, but you can't get at the information.
If you disconnect it, you lose access to it.
Excuse me?
If you disconnect it, you lose access to it.
Yeah, which means that somebody has opened the box and stuck their hand in, and they have physical access to the system.
You can do a denial of service.
If it's gone that far, you're already in big trouble.
You have physical access, you can do a denial of service. Sledgehammer.
Sledgehammer.
Yeah, I mean, so, yeah.
You got big problems, you got physical access.
Yeah, right.
What type of encryption is
There are several, and we're not going to discuss about the specifics of the encryption logic. 140-2 level 4 is the certification.
Dash 4, you say?
No, FIPS 140-2 security level 4. Look for the CMDP. Yeah, CMDP got this stuff out.
Well, we can talk about the encryption algorithms that are available. Chris can talk to that. But which one is going to be specifically used for the disk is something that we're not going to talk about. Okay? Also observe that there are 2 Ethernet connectors on the card. And this just shows that the card sits on a PCI Express bus, the typical COTS computer block diagram. And there's the card sitting in a motherboard with its anti-tamper protections removed. Here's a comparison between the IBM secure coprocessors and the Shield, which is the one that we're talking about this evening. Now, Steve was one of the designers of the IBM 4758. Steve, can you raise your hand? Mm-hmm. So Steve was one of the designers. The other designer, who's also a consultant in this project, is Dr. Sean Smith up in Dartmouth. At the time that they did that design, that card was the first one to attain FIPS 140-2 level 4 certification. And there are, I don't know, maybe there are only 3 cards that have that level of certification. Use it on a PCI instantiation, plug-in instantiation first, and then to seek funding for an integrated motherboard, and to also look at changing the form factor so that the same basic technology will work with militarized systems, which means the military uses a form. This is this card corresponds to a PCI full-length card. There's a specification for that. The military uses something called SEM-E, which is a standard electronic module. SEM-E-E is the one that's most popular. It's a standard electronic module form E. And it's a card about that big, and it has different backplanes. The backplane architecture there, it uses something called a high-speed data bus, a TM bus, and a Pi bus. And that's what most of the more recent systems are built with. And there are additional militarization requirements with that card that go beyond the PCI Express standard that we use here. But that's another.
Only Linux can use that?
Well, okay, so there's Linux in 2 flavors relative to this talk. There is Linux in the sense that there's it's possible to run an embedded Linux on the card. So that gives you the capability to run a full-blown multitasking operating system on the card. And then there's Linux, which is the host computer operating system that you're going to protect. But neither of those 2 are chiseled in stone. The protection of the host Linux, the capabilities I'm about to talk about, says I take my knowledge of the target operating system and I design defense